What's going on, guys? Today we're working on a few projects, one of which is one of my favorite devices to work on. So there are several ways how the recovery can be approached, and I always advocate for repair over the recovery approach. A lot of people ask why in the comments, and the reason for that is that repair gets you to a point where your device is functional all on its own. The last state that it was running in, that's what you bring back to life. So everything that was on it the last time it worked should come back if the unit is revived. With the recovery of the chips, we're going slightly different route. And in the best case scenario, we end up with the same thing. But that same thing isn't really promised to us. We're heavily relied on how clean our image ends up being. We may be able to read some chips very clean, but in some cases there are stubborn chips that will not read without errors. And those errors are being handled through the hardware when the device is running on its own in one way, but through our hardware when we're working directly with chips in a different way. The factory read, retry, power, and everything else that comes with original design of device is optimized for perfect, flawless work of the unit. We are trying to recreate similar conditions to accommodate the memory in order to unlock everything that's on it. The best analogy I can say for chip off is like putting a puzzle together. When you're putting a puzzle together, what is your first step? Your first step is always going to be emptying out a bag of chips, putting them down on a table, floor, or whatever you're going to use for your assembly surface. And the first thing you're going to do is you're going to flip all the chips that don't face the picture side up. That process is very much like error correction process in a chip off recovery. Error correction is when you're taking sectors that are not good and you're flipping them over to make them good, ready for the assembly. If we can't correct a certain sector count, that sector count is going to be bad for the logical image. It would be as if we didn't flip those chips upside down. So the more of these sectors we have, the harder it's going to be to produce a beautiful picture that makes sense at the end. I would always try to bring the device back to life first, unless it's just not reasonable. To help this video, please leave a thumbs up and a comment in the section down below. I'd really appreciate it. Enjoy the show. So looks like I got 3 things to do today. We'll start with this one. This is a Lexar 32 gig card, one of my favorites. Consistent problem with these things, and that problem is separation of the chips when they get bent too far. So see, the device needs to be split carefully. First thing we check is the back of this thing to make sure there are no fractures in here. If you put something around and apply a little bit of pressure, you'll see any separation if there is any. But most of the time this chip gets it the most. Because the bulk of the controller belongs to the second chip, so this is less flexible than this part. Flexes the most right here where it ends, because this board is super thin, very flexible, but because there is a controller on here and that isn't cracked, we got this happening. You see, I apply a bit of pressure to it and chips are starting to lift. So when it's plugged in, if you look here, alright, so we got flexing part right here. So that's like exactly where the pressure is going to come if the card is in the card reader. Because if I grab a card reader, show you how far this card goes in. Let's just draw like an imaginary line on where the split is. The split is right here along this edge. So we notch it right here. How far does the card slide in? See, it gets right in there. That's like exactly where it's going to bend, in that spot. So that's why it breaks off like that. The solution is fairly straightforward. We can either repair the card and reuse it, or we can take these chips off and read them directly. PC3000, flash extractor, VNR, pretty much any of these tools can handle the job very well. Let's clamp it into the jig and inspect the device underneath the microscope. This is the chip number 1. Take a little bit of flux. And heat. So key thing here is not to apply too much pressure on the device, just enough to not let it fly away, because as soon as we apply pressure with heat, this board is just gonna buckle into a bow shape. So we want to make sure there's just enough to keep it in place. Looking at this board here, it's way too much work for what it's worth. We got one, two, three, four, five, six, seven. Like the entire bottom row is gone. This one is almost entirely gone. So we got like a quarter of all of the pins is missing that are essential. Redoing this, there is no purpose in that. It's just gonna take too long. So in this case, I would just opt for chip off. It's gonna be easier and faster to get it done that way. Well, let's just go and clean up these chips, set them into the reader, and get the project done. 32 gigs is not going to be a long time consuming case. currently have 235 set up on it. Let's go 240 on it. There we go. 2.4 solid. Alright, so this is chip 1. Alright, let's let it run. It's gonna take about half an hour to read it, and then once it's done, we're gonna have to do the same thing for the second chip. So the card is 32 gigs, right? You did notice that it's a 32 gig card, and the ID is 32 gig ID. So half of this card is disabled through the controller, so that it's the same type of device, but pre-shrunk sort of thing. By vendors, so that they don't have to build a separate device, they don't have to order different components. Everything gets done on the same production line, but instead of having one product in the end, they end up having two, a 64 gig unit and a 32 gig unit. So finishing up on the second chip, almost done. So the error correction is finished for the second chip also. Card belongs to SD61 design, and looks like we already have a matching set of ID on the same configuration for the chip count. So we got two chips, one bank inside of each. If we hit this unlock button, it gives us all the options for this ID, but with the lock on, these solutions only apply to cases that match up by ID and a number of members. So knowing that this is a SD61, I'm going to select that, and the entire sequence of the assembly is already in place. Calculations for the assembler are already in place, unless we have something strange and something weird about this device. Now, what I wanted to mention is that we may have a problem, and if this model requires a cut element, because this is a downsized device. It's not a 64 gig unit, it's a 32 gig unit by actual capacity. Physical capacity is 64, but logical capacity is only 32. So that might be a problem if the solution requires that. But because we already have it in place, I ran error correction on the device. So if you have the error correction set to check, we can review how clean the image turned out to be. There wasn't a whole lot of data on here according to what the map is showing. Most of it is gray, but those blocks that are consisting, those blocks that have some data in them, they are all green on both members. We don't have any red anywhere. Seems pretty good. This is the final joint piece. So now if we go into the assembler and open up the image, we can see our boot sector here, MBR, FAT32. We got the root directory, and we got the camera folder. Now this camera folder has a bunch of NEF images. So some files here that are damaged. You see, when we have a file that has data, it shows the header. These are hitting into erased, so maybe those are deleted images, maybe there are some conflicts. Let's see if conflict auto will provide any sort of insight. For the conflict check, we've got to run it in the off mode. Yeah, so there was a conflict solved. So we did some additions to the assembler. Let's see if we have these now, and now they're gone. So it updated where those files should be located, and as you can see, the red headers on the files are no longer here and the recovery should be good. There's 20 gigs and it looked so empty. It's probably because we're looking at a combined physical image at this point, where it only looked like 1/3 was filled. But 20 gigs out of 32 is more than half. So that should explain it to why there's only 20 gigs of data, but why there's 20 gigs of data, but there was so much empty space. I hope that makes sense, but the case is successful. Yeah, thumbnails, all good. So that's how these problems are handled, guys. And if you need help with your unit, please let me know. Link to our website in the description where you can request a service and we'll reach out and help you out. Thank you very much. I'll see you all in the next episode.